All right, lecture 6, hydrostatic forces on curved surfaces. So we're going to apply the hydrostatic law to evaluate magnitude, direction, and location of the resultant hydrostatic force on curved surfaces. I'm going to go ahead and say this out front. This is usually my students' least favorite lesson in this entire course. I will also say that I think, in a lot of ways, that this is easier than the other ones. So like, what we did last class, we did hydrostatic forces on planar surfaces. And in some ways this is easier because ultimately we're going to break it down. It's always going to be rectangles is what it's going to boil down to. It is always going to be more time consuming than the planar surfaces, however. But without, belaboring the point, I don't want to pretend like any of this is easy. This is not easy. And so, just kind of bear with me, I guess. What I'm driving at is just, don't get lost in the weeds. Accept the fact that this is kind of difficult, and get prepared to fight through it. Okay. Once you work a couple of these, you'll see that to some extent these can almost be considered cookie cutter once you've done them a number of times. The other thing that I always also remember about this, there was a magic in this, and I'll bring it up to you, where when I saw how we generally solve this, I was like, oh my God, that's genius. Okay, so let's get to the genius part. Okay, so let's do some drawing. All right, so what we're going to do here, and again, this is a step up, and it's a little bit, it's really confusing to even think about. But what we want to do is we want to evaluate, for this particular problem, we want to evaluate the force on this kind of like, what do we call this? Like a quarter circle right here. Okay, so the quarter circle that is underwater here. Okay, and so what I'm going to do is, this is just a derivation, and I'm going to derive how we kind of get at that. Okay, and the problem here, if you can imagine, is that so anywhere along that quarter circle, we can figure out the pressure by, say, like right here, what's the pressure? Okay, hopefully right now you know that the pressure right there is gamma h, okay, with h being the depth from there to the surface. The gamma right here, okay, at the bottom here, is also gamma h, but h is a lot bigger. Okay, now in all cases the pressure is perpendicular to the surface, and so I can kind of draw it. I'm not really going to be able to do a good job with this. Your textbook can do this much better than I can, where the pressure is increasing with depth, okay, as it goes around that bend. Okay, so the deeper you are, so obviously like as you move from, say, here to here, the depth hasn't increased very much, the pressure hasn't increased very much, but then as you make it around the circle, the pressure is going to increase a little bit faster because you're now moving more downwards. Okay, so you kind of like, hopefully some part of you is like looking at that going like, wow, that's difficult. Okay, and it is, and what we're going to do here is we're going to derive this. We're going to derive a way to do this so that this is going to come out a little bit easier. Okay, so the first thing I want to do, besides getting rid of all of that stuff I just drew, okay, that's just something for you to think about and be aware of, is I want to label this thing a little bit so that we have some variables to work with. Okay, so I've kind of labeled this a little bit just so that we can, stare at it and make sense of it. But basically this semicircle, it doesn't have to be a semicircle really. This actually works for any random shape, but for this case, actually, we're not even going to define it, but let's just, you could think of it as a semicircle if you wanted. Okay, and this whole thing has a dimension into the board, a width of, I'm just going to say it has a width of y, okay, so a width of capital Y, okay, and usually when I do these capital Y's, I put these little, serifs on it because it's just something that like it's probably going to go away or we're not really too concerned with. So what I want to do now is I want to think about, so it may have occurred to you at this point, based on my drawing earlier of the pressures on this thing, which maybe I'll kind of briefly like redraw in there as best I can, is that the way to do this really is calculus. Okay, the way to do this is to integrate the pressure over this entire shape. And some of you immediately are already going, oh my God, that looks really hard. And truthfully, that is very hard. And that's what this derivation is about, is finding a way to not have to do that. And so what I want to do is I want to zoom in on like a little slice of this semicircle or whatever. So like if you imagine a little slice like this, okay, and I drew it a little bit big, right there. But I'm going to blow it up in a second over here to the right. And so we're going to look at this little slice, okay, which in the differential sense could be thought of as a straight line. Okay, so now I'm drawing a triangle. Okay, and it's got a pressure on it. Okay, and that pressure is determined by the depth of the depth of that location. But it's coming down at an angle theta. And the area of this, so it's got a pressure. Okay, and it's acting on this face, which is a little differential area, dA. Okay, and we note that from the trig, here I'm going to zoom in on this guy so that it's not so far away. Okay, so we'll note that this angle right here is also theta. So we will note that this dA, interestingly enough, okay, it's a kind of like a sliver, okay, into and out of the board. So it's got a width of y, right? So I'm talking about this face right here. Okay, let me kind of do it in blue, I guess, right through here. So that face right there, it's got a width of y going into and out of the board. And it is I guess, we don't really define this, but maybe it's like a ds, okay? So that's the distance from here to here. Okay, fortunately, we're not really going to use that. On this side, however, we've kind of got like this face, the vertical face, right here. Okay, it's got a size of, let's get that white again, dz times that y into the board. And this one right here has a force of, y dx, okay, where dx is going from here to here, and dz is going from here to here, okay, and the y is into and out of the page. Okay, so cool, right? Cool. Okay, so what we want to do now is I want to define. So let's say, okay, so we say the pressure, or really a differential force on this little sliver is P times D A. Okay, and we note that based on at a small enough scale, we could say that we're just going to do this. We're not going to do this in the x direction. So if I'm going to say df in the x, we're going to split it into two directions, and then we're going to kind of deal with it from there. So right now I want to do kind of like a, if you want to, you think of it as a force balance in the x direction. It's not really a force balance. But basically I'm thinking about the force from pressure in just the x direction. Okay, so it's dfx. And then basically this is going to be P, instead of dA, I'm going to have kind of this side right here. Okay, right here. So P times y times dz. Okay, so we're going to go from there. And the next thing we want to do is, okay, don't worry, we are going to get to the y direction soon enough, is, what's the pressure at this point in the fluid? What's the pressure? Okay, I want this to be screaming out in your head. What is the pressure, okay, of a hydrostatic fluid where gamma is constant and the pressure at the surface is 0? It's always the same. Okay, gamma H, gamma H, gamma H. Okay, repeat that to yourself, or rho GH, for those of you who are following Connect. Gamma H and rho GH are the same thing. Why? Because gamma equals rho G. Okay, so, all right, so the pressure is gamma times H. Okay, now we've got a Y here, and we've got a DZ. Okay, so now we're getting somewhere. Okay, let's see, what can we do here? I think we should probably integrate this sucker. We want to know the total force on this whole face as we have it over here. Okay, so let's go here. So I'm going to kind of delete some of this business because, we don't want to see all this business. I mean, we're not anti-business, of course. That would be silly. Yeah, so here's our lines. So basically, I want to integrate this, this little expression over here from Z1 to Z2. Okay, so we're going to zoom back in over here. Okay. And let's see. So on this right-hand side, I'm going to get f of x, okay, equals. And, okay, so, well, the gamma can pop out because the gamma is not changing. The y can pop out, and now I've got the integral of h dz, okay? And I'm integrating z from z1 to z2, or I'm integrating this whole thing from z1 to z2, okay, or z2 to z1, however, you know, whatever, okay, here we go. All right, so now what happens is this becomes fx equals gamma y, okay? Not forgetting our little serifs, because that remind me that this is just some sort of like, not a dummy variable, because that would be rude to call it that. But this becomes h, so the depth here becomes h squared on 2, because h is a function of z. Okay, and we're going to go from, we're going to do that from z2 to z1, z2 to z1. Okay, so this is pretty ugly, right? So we're going to keep going, and we get fx equals gamma y. Okay, and if I plug this in, I end up getting something quite ugly. Okay, z2 squared minus z1 squared, okay, divided by 2. And you're kind of like, okay, Wagner, how does this help? You think that this was easy? I do think this was easy. Well, I don't think this was easy, but I think that the result is going to make our lives easier. And I'm going to show it to you right now. Okay, so this is the magic. Okay, now I've got a 1/2. I'm going to kind of split this in half. So one thing is going to be z2 minus z1, okay? And the other half is z2 plus z1, okay? That's just factoring, and we divide by 2. All right, so now, like that still doesn't help us. All right, so nobody in my classes ever gets this, but let's do it anyway. What's z2 minus z1? Let's look over here. Okay, what's z2 minus z1? Yeah, we're waiting. Okay, I'm being a jerk now. Z2 minus Z1 is capital H. Okay, so that's cool. So we've got gamma. We've got, what order do I usually put it in? I'm just going to leave it like this, I guess. Gamma Y. Okay, Z2 minus Z1 is a capital H. That's cool. What is Z2 plus Z1 over 2? Z2 plus Z1 over 2. Well, let's go look at it. Okay, Z2 plus Z1 divide by 2. What happens if you take two things and you add them up and you divide by 2? Well, you get the average. Okay, the average. Now, what do we want to call that? Okay, now what I want you to do is this. Okay, I want you to imagine that you're swimming here, and you've got you're swimming here, and you look at the projected area of this shape, okay? So imagine you have no depth perception. What can you see of that shape right there? It's going to look like a rectangle, isn't it? Okay, you have no depth perception. It's going to look like a rectangle, right? And Z1 minus Z2, this average point right here of that rectangle is the centroid of this projected rectangle. Okay, so let me repeat that because that's very important. Okay, so this projected rectangle, okay, with a height of capital H and a width of, so going into the board, however far it goes, of y, y by h, that rectangle, the centroid of it, which of course in this case is running, it's probably actually in the center here, but we're not worried about the lateral centroid, just the vertical centroid, is, okay, is Z1 minus Z2. Okay, so that's going to be H bar. Okay, that's the distance from, so this is H bar. Boom, H bar. Okay, and we learned that on Tuesday's lecture. So if we go down here, Z2 plus Z1 over 2, that's H bar. All right, cool. All right, so now one nice thing that comes out of this is we can do this. Okay, if I put these two next to each other, okay, gamma H bar. What's gamma H bar? Oh, well, let's see. Well, gamma H from earlier, well, that's the pressure at any location. So gamma H bar, that is the pressure at the centroid. So that's P bar, pressure at the centroid. Sweet. And then what's Y times H? let's go back over here to this fancy business. What's y times h? Well, we've got this blue shape I drew. What's y times h? It's the area of that projected rectangle. Okay? So, well, that's cool. I mean, to kind of give you an idea, if I were capable of drawing this in 3D, this would go off this way, this would go off that way. There'd be like a little bit like that, right? No. Nope. Like that. Yeah, that's kind of what it would do. Anyway, so the projected rectangle would be, this is the projected rectangle. Let's pretend I didn't do any of that. I can't draw in 3D. All right, so anyway, so that's the area of, what I called, or what I'm going to call AX. Okay, AX. Okay, so that's the area. If area had to have a direction, since this area is in the YZ plane, it is the area X. Okay, so that comes out nice and pretty. Okay, you could also make it gamma H bar A. Okay, and that's, I think, probably how it's usually drawn. Oh, I used the bars. Okay, let's. This needs to be a centroid, right? So sorry about that. I forgot about the differences in the book. So this is H sub C, so the height, the depth of the centroid, and this one down here is going to be, I guess, depending on the book. So your book will do it like this. Okay, gamma depth of the centroid times area of X. Okay, it does look like your book is just going to call this area X just like area. I think it's important to note that this is the area, in the horizontal direction. All right, so the last bit here is thinking about it in terms here. I kind of want to derive at what this is. So what I want you to do is, if you go back and you look at your notes from last class, you can use any one of these three kind of versions of this. This is the horizontal force on the projected horizontal face. Okay? Meaning, what this means to me is this, okay? And before we go over to the other, and do in the y direction, is this. If I want to know, for example, in this problem, if it will let me zoom, if I want to know the pressure on this side of this, if I could draw on this kind of curve here, okay, going from there over to there, whatever this face is. If I want to know the horizontal component of that force, well, I can just find the horizontal component on this thing right here. Okay, that's a lot easier, right? Because all I need to know is like, well, what's the, how tall is this thing? Okay, well, it's H. How wide is it? Well, it's Y. Okay, so the horizontal force in this thing, oh, okay, well, let's just go, well, how deep is it? Well, that's going to be Z2 minus Z1 over 2. Okay, that's the centroid, right? So that's, and then gamma times the depth of the centroid times the area, H times Y. Okay, that's a lot easier than integrating this, whatever's going on with this curve. Okay, so it's pretty cool. So pressure at the centroid times the area over which it's acting. Okay, and hopefully we can come up with something kind of nice and clean like that for the vertical. Okay, so let's see if we can do that, and let's see if we can also do that without taking too much of y'all's time. All right. So similar to this other way that we just did the x direction, let's do the y direction. So dfy, not y direction, you bum, the z direction, okay, equals pressure times y times d, this would be dx, okay. So again, if we look at our figure, we're kind of looking at what's going on right here. Okay, so some portion of this pressure force is going downwards. Okay, and so that's the the portion we're looking at now. All right, so so what we will do here is dfz equals, well, what's the pressure? Come on, what's the pressure? It's the hydrostatic force. The pressure at the surface is 0. Gamma is constant. Okay. It's gamma times whatever that depth is. Okay. Now, then we've got, okay, y dx. Okay, y dx. Okay. So maybe we integrate this sucker. Okay, so we're going to integrate this. Okay, so we've got it at a, like, this is like at a, little differential thing right here, but we don't want it there. We want it over this whole thing. So we're going to integrate it from, we're going to integrate it from x1 to x2. Okay, so let's go back over here, and let's see what happens when we integrate from x1 to x2. Okay, so, well, let's see. So when we integrate, the first thing we're going to do, I guess, is we're going to pull out, we're not going to try to move everything. We're going to pull out the gamma and the h. So this side becomes Fz equals, okay, let's see here, gamma times the y. Those two things are constant. And then we're going to have, we still got this h, and we've got a dx. Now, what's the problem here? The problem is the depth in this case, and we're going to go from x1 to x2. Okay, and this is problematic, right? And I've never, when I teach this in person, nobody has ever been able to tell me what this is. Y times the integral from x2 to x1 of h dx. Okay, so just kind of stare at it, pause it, think about it, go look at the drawing, and then see if you can think of what y times the integral from x1 to x2 h dx is. I'm gonna sketch it real quick because I think it's kind of important for you all to get some. So this is just some shape, and here's x1, here's x2, and both of these are kind of going up to the surface like this, right? And so h is defined here. This is h. And dx is like a little bitty guy like this. Okay, and y is the width of this thing going this way. Okay, also going up to the surface. Okay, so maybe there could be like a little spot like that too. I shouldn't have drawn that. Okay, as usual, I screwed this up. Anyway, so it should be like that. There you go. Okay, so the question is, what is all this? Okay, so this is a little dx. Okay, again, I've never had anybody who could identify what this was, but here it is. Okay, so here's a little dx right here. So I'm going to take that little dx. I'm going to multiply it times h. So now I've got dx times h, so that's this area right here. Okay, the area of this little tiny triangle, right? Okay, it's got a height of h and a width of dx. Okay, I'm going to integrate that from x1 to x2. Okay, so that's going to give me this whole front face. Okay, because now I've integrated it over the whole front face. Okay, now I'm going to take it, and I'm going to multiply times y, and now I've got this whole volume here. Okay, hopefully that makes sense to you. And my drawing's not really that terrible in this case. So what's cool about this is Fz becomes gamma times the volume of water above the your curve. Whoa! How cool is that? Are you excited? You excited? You're probably sleeping like my dog. Isn't that right, boy? Anyway, my dog is just sitting there yawning. He hates, I'm doing this during office hours. He hates office hours. He's a good-for-nothing dog. But we still love him anyway. So, all right, so what's cool about this, and this makes perfect sense, actually, because we take gamma times the volume. Gamma is weight per volume. If we multiply times volume, what do we get? We get the weight of the water above, our shape. Well, that makes perfect sense, doesn't it? Okay, so basically, what is the, all of the pressure of all the water, what's the net effect of all the pressure of the water above this curve? Well, it's the same thing as the weight. The pressure, the weight is what causes the pressure, or however you want to look at it, but that's what it is, right? So if we just calculate the weight of this whole thing up here, well, we're good to go. Okay? So that's actually logical, right? You didn't need to take this class. Somebody could have just told you that. You know, what does this thing have to support? Oh, it has to support the weight of the water above it. Okay, so whatever this shape looks like, you know, it has to support the weight of the water above it. Cool. Okay, so I'm sure you're not as excited about this as I am, but every time I do this derivation, it actually works out. It's pretty cool, right? All right, so you know, these derivations can often fail. I'm sure you've had professors fail in derivations in class. I don't want to be one of those professors, but I've done it before. So maybe I am one of those professors. All right, so the last thing about this is that here's the general approach, okay? So that is all very cool. However, the volume of this water above it can be a little bit complicated. So here is how we typically do this, okay? And so all that noted, here's how we typically, how we normally do this, okay? And then I'm going to work a problem, how to do this in general. Okay, and what's interesting is that your textbook has the exact same figure that the old textbook had, which is, let's imagine we have something and it's like a weird shape like this, okay? And well, this is just kind of like going off into wherever, okay, and it's full of water, okay? And you're assigned to figure out what is the force on this thing. Okay, usually this is going to be something that's defined by an equation. It's not going to be random like that, but whatever. This is the way your book drew it, and this is the way it's typically drawn, okay? So what you're going to do is you're going to slice this thing like this, okay? This is usually called a control volume. And what we're going to do is we're going to look at this. So we want to know about this gate right here, or this wall, or whatever, and it has whatever random shape that it has. And so what we're going to do is we're going to draw a line vertical from its, you know, X edge and horizontal from its Y edge. Okay, so that I can get something that makes sense to me. Okay, and now what I'm going to do is I'm going to draw a free body diagram of that random shape. All right, here we go. Free body diagram. Okay, FBD. All right. Now, what's the pressure on the top of this random thing? Okay, if you're not saying gamma H yet, you're making me angry. Okay, so here it is, gamma H. It's all along the top. The thing is, okay, right? But right now, because the depth all along the top is the same, okay, then the force all along the top, it just depends on the same constant pressure. Okay, what's the pressure right here? Okay, if you're not saying gamma H, I'm getting aggravated. Okay, so now we're going to go down here. What's the pressure right here? Well, it's gamma H. H is more, okay, because the depth is deeper. So there you go. So on this side, the pressure increases because this face is getting deeper as we go down. Okay, so we got pressure on this side. All right. Okay, now we've got so this third side right here, it has to push back. It has to answer all of that. So it's going like this, okay? So and then the pressure is gradually getting deeper. Obviously, I'm not very good at drawing pressures. But this force right here needs to be the same as that one because they have the same H. Right, good. All right, so remember, what's the pressure? Gamma H. Okay, so here we go. So this is going to be like as best I can draw it. Actually, that's not too terrible, okay? So everywhere the pushback on this wall is going to be perpendicular to there. All right, cool. All right, now last thing. Okay, I'm missing a force, right? So there were three edges to this thing. Everywhere where there's an edge, I need to think about surface forces. So the surface force here is a pressure. Surface force here is a pressure. Surface force here is pressure. So I got all my surface forces because there's no shears. There's no shear in a static fluid. So what other force do I need? You're right. You're right. You're right. I need the weight of the fluid right here. Okay? And that's how you do it. Oh, let's redraw it. Okay? And let's And let's redraw it one last time. And what we're going to do when we redraw it is I'm going to take all of these pressures and I'm going to replace them with forces. Okay. Oh, you know what? I'll just do it like this. Okay, so I've got an FV right here. So that's a vertical force from the top. I've got an FH right here, okay, acting at the center of pressure. And then this whole side, all of this pressure, which we don't really like because it's very confusing, is just like somewhere in here, okay? And we could call it F of the wall, we could call it just F, we can call it whatever you want. But ultimately what you're going to want to do is you're going to want to replace all these, do some statics, and get theta right there. Okay? So we are at about 30 minutes right now, and so what we're going to do from here is I'm going to work one of these problems start to finish, and I'm going to show you how to do all this. Okay? If you were able to do the the planar forces, then that's all we're doing here. Except we've, in some ways, simplified it because we will not have difficult planes, right? I'm never going to have a triangular face this way. I'm never going to end up with a semicircle or a quarter circle or anything like that. All I'm dealing with is, like, if you think about this top face, for example, okay, this is all going into the board. So the top face is a rectangle. This side face right here, it's a rectangle. Okay, now this face over here, it's something really ugly. Okay, there's no way around it. But the thing is, usually we don't solve for this face. We just do the statics to get F. So we don't have to figure out the area of that. Okay, the weight here, okay, the difficulty with that weight is that this shape is unusual. Okay, so the weight is going to be applied at the center of mass, okay, or the centroid of this front face. Okay, and so that's important for the statics. Okay, let's just do one, and hopefully this will make sense. Okay, so let's see. We're going to find some nice blackboard, like right over here, and we'll pause for a second while I draw a pretty picture. All right, so here's my drawing. Not so pretty, maybe, but it's the drawing I got. So let's see what's going on here. So we've got. We've got a wall on the right here. We've got a sea floor, and for some reason, somebody wants to know what the force is on this quarter circle. So we're talking about the quarter circle from this point right here to that point right there. Okay, and we've got some dimensions. We should note that this quarter circle is 5 meters wide, so it goes into the page 5 meters. And I guess the circle itself has a radius of 2 meters because it's 2 meters tall and 2 meters wide, or 2 meters left to right in the x direction. All right, so how do we begin? Okay, so what we're going to do in these problems always is we're going to draw a free body diagram of the water. Okay, so this is a free body diagram of the water. Okay, and it's kind of like the water that, if we're going to cut it out. So like if I was mowing lawns, and I had a little complicated section like this with a curve or whatever, I used to kind of make straight lines out of the whole thing. Like if it was a curvy section, I might do this little quarter circle first, because then the rest of the day I can just, go back and forth and I don't have to worry about anything, right? So this little quarter circle right here, we want to look at the water that is contained by that quarter circle. And we want to cut it off in such a way that we've got flat planes that are in the x, that are horizontal or vertical, because those are going to be easier for us to work with than anything else we might do. Okay, so what I'm going to do is I'm going to draw the free body diagram, and I'm going to try to draw this in 3D. I'm going to mess that up, so I'm going to pause it because it's going to take me a little bit. All right, so I don't think this is really that terrible. Okay, but anyway, so this. I've made it a little bit larger so we can see it, but this is 2 meters in this direction. This is 2 meters in this direction. Okay, and then from here going back into the board this way, that's what we say 5 meters. Okay, so that's the 5 meters wide. Okay, so now we want to analyze the forces on this thing, and we kind of want to. So the first thing we want to think about all the forces on this sucker. Okay, so anytime we do a free body diagram, that's the next thing. So the first thing we want to do, and I'm going to draw them all in this front face, even though they're not actually happening at the front face, right? They're happening some distance into, well, maybe we won't do that. Let's do it on the front face. Okay, so on the front face, here's the weight. Okay, it's actually technically happening 2.5 meters in to this thing. So, you know, maybe if I were to like march this back this way and put it like right in there, maybe it's like, let's just put it right there in the middle. Okay, that's where the weight is happening. Okay, anyway, so that's the weight. Okay, it's happening at the center of mass of this sucker. Okay, what else do we have? Well, we've got pressure on this face right here, on the horizontal face, or really the vertical face, I guess, and it's happening maybe like right here. And it's actually probably a little lower than that, isn't it? So let's go ahead and put that right there. Okay, that's FH. Okay, the horizontal force. We've got a vertical force which is acting on the top face, so it's happening right here. So we'll call that FV. Okay, and then the last force we have is the force of the wall itself pushing back. Okay, and that's ultimately the force we're looking for, right? Because if we find this force right here, which we call F, okay, wherever it's acting, if we find that force, then we know that the total effect of all of the water is the opposite of that force. Okay, so what we're going to do is we're going to think about these shapes. Okay, and so every time I do this, I always think about shapes. Okay, and so what I'm going to do is I'm going to do shape. Okay, and the unfortunate thing about this particular problem is the shapes are the same. They have the same shape. As in they're rectangles, and they even have the same dimensions, which is unfortunate, but that's just, you know, when you deal with semicircles, it makes things easier. But I want you to keep track of the 2 meters that I'm using when I use 2 meters. Okay, so the first shape that I'm going to do is going to be the vertical shape. Okay, I'm going to do vertical rectangle. Okay, so if I look at this vertical rectangle, okay, the dog is very excited. If I look at this particular vertical rectangle right here, okay, what I want you to do is I want you to think about the things that we need when we're doing these shapes. Okay, so we need the depth to the centroid, which is h sub c, according to your book, although in my notes you'll see h bar. We need the distance to the centroid along the face of this shape. We'll need the moment of inertia, I, X, X, comma, C. That's a really annoying notation. And we're going to need the area of the shape, okay? These are the things we need for that vertical rectangle. Okay, we're going to need those for all of these things. So I could say vertical rectangle, and right here I could have the horizontal rectangle. Okay. And that's actually, in this case, not all of the shapes. So we'll talk about that as we go. All right, so HC. So, well, let's just do the area of this rectangle first. So I think if you look at this drawing, you can see that the area of the vertical rectangle, that's the one that I've kind of highlighted in blue, in white. That one is 2 meters by 5 meters. So that's 2 meters times 5 meters, okay, equals 10 meters squared. Okay, cool. All right, okay, sorry. Wrong location. All right, so now we need the depth to the centroid, okay? And so for this, our free body diagram isn't really very helpful, okay? But it's a rectangle. So if you go to that table in your book, I think it's figure 332 or 320, whatever it is. If you go and you look at that, for a rectangle, it's halfway down the rectangle, okay? So it's like right there. Unfortunately, right there, we need the depth. We don't need the location. We don't need it's halfway down. We need it from the surface of the water. So I'm going to start. So here we are, and I'm going to go up to the surface of the water. Okay, and so that's 4 meters plus 1 meter. That's 5 meters. Okay, so that's 4 meters, and then we got halfway down the rectangle, so that's 5 meters. Okay, now YC, on the other hand, it starts at the centroid, and it follows the face, until you hit the surface of the water. Okay, so in this case, it's the same thing as the HC. Okay, pretty cool. All right, and then the IXXC, which, I'd like to pretty that up a little bit. Apparently, This does not like me to erase. Okay, so off of that same table, if we're looking at a rectangle, it's going to look like this: 1/12 base times height cubed. I think your book uses AB cubed. I prefer base times height because B reminds me that, that it matters which face is which. So if I look at this rectangle, it has a base of 5 meters and a height of 2 meters. Okay, so it's going to be equals 1/12. Oh, that's not a 12. Base 5 meters times the height, which is 2 meters. Okay, cubed. Okay, equals. Okay, 2/3 of a meter to the fourth. Okay, cool. What about the horizontal rectangle? So that one, which I'll highlight here in, we'll do green, I guess. Okay, is this, okay, this is the top face right here. Okay, and why am I doing this face? Well, I'm doing this face because I'm trying to get at this force right here. Just like just now, I was doing that other face because I was trying to get at FH. Okay, so so what we need to do is give myself a little bit more space with this magic thing. Okay, and we're going to do these same things on that shape. And there will be a hiccup here. There sometimes are hiccups. The hiccup actually makes your life easier in this case. IXXC and A. Okay, so noting, if we go and we look at that green shape, okay, it's 5 meters by 2 meters. Okay, so it has the same area as the other one, 10 meters squared. IXXC, ooh, well that's 1/12 base times height cubed. Which one of those is the base and which one of those is the height on a rectangle that's flat? Problematic. Okay, question mark. All right, HC. Okay, well, where's the centroid of that rectangle? Well, the HC is right here. Okay, and the rectangle, it's right in the middle. Okay, it's halfway in the width and halfway in the length. So what is the depth of that thing? So if I go over to this drawing, I can say, okay, well, it's right here. What's the depth to that point? Well, we're going to go from there all the way up. Oh, it's 4 meters. Okay, 4 meters. Cool. Okay, what's the YC? By the way, my classes always get the YC wrong on this one. What's the YC? Okay, pause it and think about it. Okay, are you back? All right, normally for the YC, what we do is this, right? We say, okay, cool. The YC is going to be, we're going to start at my point at the centroid, and I'm going to follow that face until I hit the surface. Okay, okay, how far until I hit the surface? Never going to hit the surface. That's interesting. Okay, so the YC here, yachi machi, infinite. Yachi machi. Okay, so that's pretty crazy. Okay, and here we're following Wagner's protocol, but we're not thinking. Okay, and so we're going to get there, and we're going to explain what's going on here, because this also throws all of my students for a loop on the test. Okay, so let's do these two shapes, and then we'll handle the weight, because the weight is also a shape. But let's do these two first. Let's just go ahead and get all of our shape business out of the way. Okay, so the last shape that we need to worry about is I guess it's a vertical. Okay, semicircle or quarter circle. Okay, now why do we need this one? Okay, let's go and look at this. Does it have any pressure acting on it? Well, it could, but we're not really concerned about it because the problem is really we're looking for this force in those two dimensions. Besides, whatever the force is on one face, it's being counteracted by the pressure on the other face. Let's draw this face in red like this. Okay, so whatever's happening on this one is being countered by the force on the other one. But the reason we need to know this is because we need to identify where the weight is acting. Okay, so if I draw a real quick semicircle like this or quarter circle, the weight is acting right here on the centroid of this thing. Okay, this quarter circle. So what we need to do is we need to go up here and we basically just need to find the centroid. So I'm going to define this kind of we'll do two things. We'll do the area, and I'm just going to call this the centroid. Okay, and I'm not going to call it the HC because I don't really want to do that. So using your textbook, you will get that the centroid is 4r over 3 pi, and this is from the flat face, okay? And the area, of course, is the area of a circle, pi r squared, divided by 4. Okay, so I'm just going to plug and chug that right now off camera to save time. All right, so now we kind of got all the geometry out of the way. Let's go ahead and start solving these things. Okay, so we've got all the faces. We've got all the kind of like stats on the faces that we need. And I mean, this one's going to be a little bit confusing for you, but here, all we care about for this one is we're trying to get the weight of the fluid above the, the curved surface, above the surface, I guess. And so all we care about is the weight and where it acts. Okay, so the area is going to help with, the centroid is going to help with where it acts. The area is going to help us calculate the volume. All right, so let's go down and we'll do these shapes, and we're going to do them one at a time. Okay, so we're going to start here with the vertical rectangle. Okay, now I want you to remember that there's only two equations that we need here, and I'm going to draw them real quick. All right, so there's this equation, and I've written it 3 times. Okay, because, well, we're going to need it over there, maybe, and maybe we're going to need it, once more over there. So we'll play with it when we get there. Okay, but right now for this one, for this particular problem, okay, we're going to do FR equals gamma. What's the gamma? What are we dealing with here? Oh, it's water. Okay, cool. So the gamma of water, we're using meters here. So the gamma of water in this system is 9810. Newtons per meter cubed. You could use rho g, by the way, if you wanted to, instead of gamma, but I'm not going to do that. Okay, HC, the height of the centroid. Well, I found that to be 5 meters. Okay, and the area I found to be 10 meters squared. Boom, done. Okay, no thinking once you put all this stuff into, into this chart from above. So now we plug all that into a calculator and we'll get a number. Okay, we're going to do this for right here. So YP minus the YC is 5 meters, and then equals I_XC, 2/3 of a meter to the 4th, divided by the YC, which is 5 meters, times the area, which is 10 meters squared. Okay, cool. Okay, again, we're ready to go. Give me 1 second. I'm going to need to create some space here. I foolishly thought this would all just, be small for me, and it didn't. All right, so if you plug those numbers in a calculator, you get the force is 490.50 kilonewtons, and that YP is 0.000 or 0.066667 below the Y of the centroid. Okay, now notice there was an error, okay, right here. You probably caught that earlier. That should have been a 10. So I had to fix it over here as well. Okay, so just, my apologies. Anyway, okay, so that is kind of the gist of what we're doing here. Okay, so this whole thing, which I will move around and I will put over here. Okay, that tells us my horizontal business. Okay, and my horizontal force and where it's acting and all that other stuff. In fact, I think I could probably, normally this is FR, and it is an FR, but I think we're going to change it and make that an FH, okay? Because in this case, that's what we're talking about. So this is an FH, if my pen will work. Okay, so here's an FH. Okay, so this is the magnitude of that force and where it acts. All right, now let's go to the horizontal face. So this is the face in green. Okay, so that's this face right up here. Okay, and this is important. We have to think about this horizontal face because remember, for some reason, I have to deal with the fact that I didn't get a value for this, for either of these two. I mean, I got an infinite value for YC. This this particular thing has screwed up generations of my students. Well, not really generations. I haven't had generations, but semester after semester after semester. So let's see what we can do. Okay, so the gamma of water, 9810 newtons per meter cubed. Okay, the depth of the centroid, we found it up here. It's 4 meters. Okay, and the area of that face is 10 meters. Okay, so 10 meters, or 10 square meters. Okay, so that's not a problem. We can plug that in the calculator and we get an answer. Okay, what about yp minus yc? We don't even have a yc. Okay, equals all this stuff. We don't even have an ixx. Yeesh. Okay, so this whole thing is like 3, riddle me this, riddle me that, Batman sort of things. Okay, so let's just go ahead and get our FR, and then we'll talk about this. Okay, 392.40 kilonewtons. All right, so that's, okay, that's, we got a force, that's good, but where does it act? Okay, so what I want you to think about before we move anywhere here, first of all, this FR, the force of resultant in this case, is our FH, excuse me, our FV. Okay, so we can rename it as our FV. But what I want you to remember here is that the whole point of this second equation is to figure out where this force acts. Okay? And the thing is, and I kind of encouraged you to do this anyway so that you would make this mess up, because I want you to remember this. I desperately want and need you to remember this. Well, I don't really desperately need you to, but it would be good for all of us if you remember this. Look at this blue thing. Okay? So on this vertical face, the reason that the force does not act at the centroid is because, let's go look at the vertical face, if this thing will let me zoom in, is that the pressure on this vertical face looks like this. Okay, so remember, if I was like trying to replace all those with a single force and I put it right here, the effect of that from a moment standpoint would not be right. Right? Because if I were to try to oppose that force, and I try to oppose it right there, then what would happen? This would have a moment like this. Right? So that's not really where it's acting. The force is actually acting a little bit below that. It's somewhere down here. Okay? How much below it? Well, we just solved for that. We went, because we said, well, yc equals 5 meters. And this is yp right here. Okay, y to the center of pressure. And we said yp minus yc is 0.0666667 meters. We just solved for that. Okay? In this case, it's not really that different, but it is different. Okay, what about this top face? Okay, well, what's the pressure right here? Okay, hopefully you're saying gamma h. If you're not saying gamma h, the sound must be off. I don't really know what's going on here. Okay, so anyway, so we got this, and what's the pressure here? Gamma h. What's the pressure here? Gamma h. What's the pressure here? Gamma h. Well, the pressure on this face is always gamma h. The pressure on this face is gamma h. But as I go on this face, h changes. On this face, the h doesn't change. So if we have a horizontal face and the h does not change, okay, where is the force that's going to, where would I put the force that's going to balance all of that? Say centroid. Okay, so if you put a force right here to counter it, look, it's evenly balanced, right? So you just need to find the centroid of that face. You don't need to do that second equation. Okay, so when you see a horizontal face, and bold this on your thing, okay? People, whenever I, on a test or something, I give a horizontal face, people get very confused, and really it's meant to be the easy problem, because it's easier to do the horizontal face. Okay, so what we do over here, if it will let me, slide, okay, is we don't care about this yp, because this is a horizontal face. Okay, because it's horizontal, because the face is horizontal. So if we have a horizontal face, we're good, man. We are good, okay, because we know that this force, the FV, is going to act at the centroid. Okay, so where's the centroid? Well, it's at, we don't really have maybe it's at, maybe it's going to be at X of pressure is 1 meter from, I guess, the center of the circle, from the center of the imaginary circle. it's only a fourth of a circle, so the center is like right there. Okay? Okay, hopefully that makes sense to you. But that is a big problem that happens a lot. All right, so the last time we do this, so that's FV. I'm just going to leave it there, I guess. And let's go ahead and zoom in over here, and let's look at these guys. Okay, so what do we have to do with, this all has to do with the weight. And so what we're considering here, I'm going to just draw it again very roughly. Okay, is we've got a fluid that looks like this. All right, so that's our fluid. All right, what's the weight of it? Okay, in fluids class, in the other class, it's mass times gravity. In the fluids class, it's a specific weight times the volume of that semicircle, right? So we're going to go, okay, so weight equals, well, this is 9810 newtons per meter cubed. Cubed, not squared. And the volume of that sucker, oh, what's the volume? Oh, well, we're going to take the area of the front face, okay, which is 3.1416 meters squared, okay, times the width. Okay, that's how you find the volume of prismatic solid. Okay, so the width in this case is, I believe we said it was 5 meters. Okay, so the weight equals, okay, 154.10 kilonewtons. And where does it act? Okay, well, it's going to act on the center of mass. Okay, so in this case, it's the centroid of this face. Okay, which I guess technically kind of runs through the whole thing in that direction. So we're going to I'm just going to kind of place it in how far is it acting off of this face right here? Well, oh, look, we already solved for that. Okay, so it's acting, so this distance from here to here is 0.84883 meters. Okay, sweet, sweet. Okay, so now all we got to do is we got to finish this problem. Okay, finish him. All right. Yeah, I don't know why I just did that. Okay, let's pretend that never happened. Okay, here's a semicircle, and we're going to draw these forces. Okay, and so we're going to use our information. So here's FH, right here. Okay, where is it happening? Right here. Okay, so it is going to be from the surface down to here is 4 meters. Down to halfway is 5 meters, and then we have to add this little bit right here. Okay, so this is going to be, so maybe it's like right in here, like this. And so this distance from here down to here is 1.066667 meters. Why is it like that? Because Wagner is a fool who makes you always keep 5 significant digits until the end. Okay, so then how much is that? That's 490.50 kilonewtons. All right, what else we got? Okay, we've got this. Okay, now we're going to deal with this vertical force. Okay, what do we got here? 392.40, 1 meter from the center of the quote-unquote circle. Okay, so it's going, we're going to start here, and we go this way, 1 meter. And there it is, okay? So that's going to be 1 meter, and this is going to be 392.40 kilonewtons. Cool. All right. Now we've got this weight, okay, which is in blue, 154.10 kilonewtons, and it's acting, well, let's go right in here, and we'll go this way till we get 0.840.883 meters. And we're going to have the weight going down this way, okay, at 154.10. Sweet. All right, what else? Oh, I should note that this weight is also happening, that same distance going up, right? So we have all of that going on. Okay. What else? So we just have this F right here. Okay, and that's kind of what we want, right? So this is the last bit. So this is like the final free body diagram. And there's one last trick here that I almost completely dislike. But let's do the easy bit first. Okay, so we've got our final free body diagram, and we'll say, okay, the sum of the forces in the x direction equals 0. That makes sense, right? So what we're going to do here is we're going to say, okay, well, what forces do we have in the x? Well, we've got 490.50 kilonewtons, minus the F force right here, which I don't know, we didn't really give it a name. I guess we'll call this F in the X direction, because X hasn't been used yet. We were using F sub H for horizontal force on the vertical face. Okay, so that equals 0. Should I use my calculator for this one? No, let's not. Okay, F of X equals 490.50 kilonewtons. Cool. Okay, what's Fy? Okay, sum of the forces, or Z, I guess, equals 0. Let's see, what do we have in the Z? Well, we've got 392.40 kilonewtons. That's a negative. Minus 154.10 kilonewtons plus F in the Z direction. Okay, equals 0. Oh, don't do it. Okay, equals 0. Sorry, the program is going wonky. Don't go wonky on me. That's a 0. That's a 0. It's too late in the lesson to have these screw-ups. All right. So F of Z then equals 546.50. Those are kilonewtons as well. Sweet. All right. Well, and we'll do the part that you know and love right here. I'm actually going to pause and just solve this whole thing for the resultant. So F then. All right. So just kind of like figuring out what this force is. We've got F, we've got theta. So ultimately we can say that, F equals 734 kilonewtons, keeping 3 for our final at an angle. That's 48. So it's going to look like this, 48.1 degrees. Let's undo that. Put a 1 there. 1 degrees. Okay. Now, sometimes, and I usually don't end up doing this, but sometimes, and this is the part that I don't like, sometimes what somebody's going to ask of you is they're going to say, I want to know where this force acts. And this can be a pretty annoying question. I don't like this part, which is why I never really ask it. Just listen and see if this makes any sense to you. Okay, so here's our F X, and here's our F Y, or Z, excuse me, F Z. All right, so we've got all of our forces on here. So one of the things to remember about a fluid is that it cannot, okay, a hydrostatic fluid, there's no shear forces. Okay, so this force right here and this force have to end up being opposed to each other exactly. Okay, because otherwise there's a shear in this fluid. If there's a shear in the fluid, then it's going to flow. It's not flowing, so therefore it can't happen. Okay, so these two forces, this one then is acting 1.06667 meters from the top. Okay? It has to. Okay, now in the horizontal direction, it's a little bit harder because we've got 3 forces. Okay, so it's clear that Fz cannot simply be directly across from the weight or directly across from the pressure on the top. Okay, we have to sum moments. Okay, and what's interesting about this is when we sum moments, we're going to pick a spot, and I'm going to tell you right now, I'm going to pick this spot right here. Okay, which I don't know, it doesn't have to be that spot. It could be this spot right here. It's just somewhere along here. And the reason I'm doing that is because all of my distances are measured from there. Okay, so what we're going to do here is we're going to say, okay, well let's figure out where this force is acting. So from point B, it's going down 1.06667 meters, and we want to figure out how far over it's acting. Okay, so let's go ahead and solve that by summing moments around somewhere on this line right here. Okay, so I'm going to do the sum of the moments around point B, sure, equals 0. Okay, so let's see, we've got the weight. So that's 154.10 kilonewtons. Okay, times its moment arm, 0.84883 meters. Okay, I've got, so that's going to make this thing go clockwise, so that's a negative. The other one, the pressure on top, so this force right here, okay, that's also going to have a negative sign, and that's 392.40 kilonewtons, okay, and times 1 meter. Okay, and then the last force is going to be our Fz plus Fz, okay, which we've solved for. So I guess I should just put the number in there, 546.4. Let's go ahead and put that in there. 5, come on, you can do it. 546.50 kilonewtons times x. I don't even know what to call this location. X. Call it x center of pressure. Okay, equals 0. Okay, and let's go ahead and solve that. Again, I'm going to go off camera. Now, you might be wondering, well, what about these horizontal forces? Well, notice the horizontal forces are right across from each other. And so one is positive and one's negative, and they have the same moment arm. So they're going to end up canceling each other out. So we don't worry about those two horizontal forces. Okay, so, all right, so let's solve this sucker. Okay, so just doing the algebra, XCP is 0.95737 meters, or 0.957 is what we're going to report. Okay, so I'll go over here, and I'm going to add that in there. Okay, so where is it acting? Okay, it's acting at a point. I prefer this to be in white. Okay, at x comma y equals, let's see, the x is, well, we just found 0.957 meters, 0.957 meters, and the y is negative 1.0667, negative 1.06667 meters. Okay, and we'll extend this box. Okay, so, and that's it. All right, so zooming in, that's the final answer. The puppy dog has decided to start barking at something, so you might hear a bark. And that's it. So that's where it acts. So if we were to go back to the original drawing, we could find that spot. Okay, we could like zoom in here maybe, and it's, you know, somewhere in here is where this F is actually acting. Okay, it's acting like right in here somewhere. It's actually probably right here because it's going to be between this force and that force. So right in here. So between the pressure from above and the weight of the fluid, it'll be somewhere in there. Okay, so this is where it's going to act, and that's it. Whew. Okay, so that's challenging. There's no question about it. But if you follow these steps, if you just kind of follow along, take your time with it, to me, the most important thing is line up your shapes. Okay, think about what's going on with each shape. And once you do that, things become a lot easier. Okay, so we'll zoom out so we can get the total picture here. And just, you know, again, take care of yourselves. Y'all be easy. Some of y'all started coming to office hours. It's really awesome. It, you know, helps me figure out what you guys are not understanding. And, you know, so, I mean, it obviously breaks up my day. I enjoy when y'all come. But the most important thing is if you need help, you're getting it. So please come if I can help you. All right, I'll talk to you later, and have a good day. Take care of yourselves, and, you know, be easy. All right, bye. Don't do it.